Okay, so welcome to our second lesson on convex optimization, where we are going to finally see the most classic type of optimization problems and try our hands on solving one of them as well. So convex problems, as we've briefly mentioned before, are super desirable because they only have one single unique optimum and therefore they are very easy to solve. So it would look something like this with a very distinguishable feature where it's a very nice valley. So the optimum or the minimum will naturally be the point at the bottom of this valley. Although convex problems are super desirable, the catch is that they are very particular as well. To qualify as a convex problem, the problem itself must have convex objective, convex inequality constraints, and also linear equality constraints. And there are actually many other types of convex problems. So within the family of convex problems, we have firstly the graph form programming, GFP, and then we have cone programming, CP, semi-definite programming, second order cone programming, quadratic programming, and finally, the smallest subset of problems called linear programming. Linear programming, as I mentioned earlier, they are very common in operational research. They're what help Amazon manages its warehouse or inventory, or they inform how manufacturing companies schedule their production as well. So they are really useful engineering optimization problems. Now let's take a closer look at two types of convex optimization. One is the linear programming problems. So linear problems basically mean that the objective is linear and the constraint is also linear. So it takes such a mathematical form. We first say that we want to minimize f times x, and subject to inequality constraints and equality constraints in this format, so ax plus b equals 0, cx plus d less than or equal to 0. So you might wonder, what is this t over there, the t symbol over there? They are actually a very mathematical way to express in the most generic form what linear problem represent. So to give you a more solid example, we can take a look at this particular problem where we have minimized minus 3x1 minus 2x2 subject to three constraints, for example, 6x1 plus x2 minus 20 equals 0. So first thing, we can see that there are no power terms, there are no exponential terms or trivial terms in here, so this is linear, the objective and also the constraint. Now, if we want to represent it in matrices and vectors, we can actually say F is a row vector of minus 3 and minus 2, as you can see in here. That's why we have a T symbol here, which is the transpose symbol. In our course, we are going to assume all of the vectors we talk about or we use, they are column vectors. So we put a transpose symbol here to emphasize that it is a row vector, because we have to have a row vector for it to be valid when we multiply it by a column vector, which is the x1, x2 in here. So altogether, basically, it means that minus 3x1 minus 2x2 is the objective function that we're looking at. And similarly, we can use matrices to represent our constraints, because constraints can have multiple constraints as well. So the capital letter A and C here are basically matrices. If there's only one equality constraint, as in the case here, our matrix collapsed into purely a row vector again. But if we have two constraints, like here we have two inequality constraints, we can actually express that part in a matrix. So we have 2x1 plus 1x2 minus 12 less than or equal to 0. That would be the first constraint over here. And the second constraint, we can read it like x1 plus x2 minus 10 less or equal to 0. So that's how we can abstract this representation into a generic form, which is represented in here, minimize f transpose x. And this is what an LP looks like, a linear objective with a linear constraint. What about QP? A quadratic program basically means that we have a quadratic objective and a linear constraint. An abstract form of it would be something like minimize a half xtqx plus qtx. So again, this is the most abstract mathematical format. So in here, you can see that we have in the first term, x transpose times a matrix Q, a capital letter Q, and we times it by another column vector, x again. This is the way how matrices can be multiplied together. And you can very loosely translate or imagine it as having x to the power 2, so a square term. That's why this is a quadratic objective function. Although it isn't really like that in mathematical terms, but you can imagine it as raising x to the power 2 by having x here appearing twice in the first term. Then the second term, qtx, is a linear term because we only have one x in there. And the q, again, is a row vector, so that it can be multiplied by the x, which is a column vector. And our constraints are basically the same as previous: ax plus b equals 0, cx plus d less than or equal to 0, where there could be multiple constraints like that. And an example of this would be something like this: minimize f equals to x minus 5 to the square. If you remember arithmetically, you can expand it so that it becomes x squared minus 10x plus 25. Then this would include the x squared term, so that would be a quadratic term over there, and also a linear term, which is just the x over there. So that's why this is a quadratic objective. And then we can also have a linear constraint, x minus 3 less than or equal to 0. Then this would be a QP because it has a quadratic objective and also a linear constraint. And you can visualize it as something like this. So this is a very typical form of a quadratic problem where we have a quadratic function here that resembles a very nice valley, continuous valley with a very clear bottom point that signifies the minimum point. If we have an inequality constraint like this one here, we would then see a shaded region that is divided using a straight line because it's linear. And this region would then be our feasible region. And you can see how simple it is to solve because we know the characteristic of this convex function. We don't even need to tune any parameters in our optimizer algorithm. We don't even need to have a very good starting point because just by looking at the characteristics, we can mathematically devise a specialized algorithm that very quickly gives us the solution. We can even solve it in one go. So that's why convex problems are very desirable. And that's why, although it's a very simple foundational kind of optimization problems, they are super important and super essential in the world of optimization.